In this video, we're going to introduce 3 more rules that can be used to find derivatives of functions. So we're going to introduce and use the sum rule, the difference rule, and the product rule. Now, the product rule is one that has the potential to be used incorrectly, especially if you're on an exam, you're feeling stressed, you're under pressure, you're very tired. So we're going to practice looking at some incorrect uses of the product rule. As the name suggests, the sum and difference rules are designed to tell you how to calculate the derivative of a sum or a difference of 2 functions. So we have 2 functions, let's just call them f of x and g of x, and we're interested in trying to figure out what is the derivative of f of x plus g of x. Again, this is one of those sort of miraculous formulas which is as simple as you always dreamed it would be. The derivative of f of x plus g of x is just equal to the derivative of f plus the derivative of g. So find the derivative of the 2 individual functions and just add the results together. Amazingly, it's exactly the same even when you're subtracting. If you want the derivative of f of x minus g of x, you can find the derivatives of the 2 individual functions and then just subtract the results. So now that we have the power rule and the constant multiple rule and the sum and difference rules, we have actually unlocked the ability to find the derivative of any polynomial function, because a polynomial function is just a sum of constant multiples of power functions. For example, here we have the derivative of a function f of x equals x to the 5th power plus 17x to the 3rd power minus 6x plus 8. So this is our first example using sum and difference rule. And when I show you my work, I'm going to show you work in a lot of detail. But as we begin to use these rules more and more often, the greater liberty that you will have to omit some written steps and to do more in your head. And you'll see me too as this video goes along. I'm going to start out writing down a lot of steps in a lot of detail, but toward the end of the video, I'm going to start writing down less and less detail. So in great detail, I'm going to try and find the derivative of x to the 5th power plus 17x to the 3rd power minus 6x plus 5. The sum rule says that instead of trying to find the derivative of this entire function all at once, you can find the derivative of each individual term separately. You can find the derivative of x to the 5th power. You can find the derivative of 17x to the 3rd power. You can find the derivative of 6x, and you can find the derivative of 5. So what's the derivative of x to the 5th power? The 5 comes down, and the power gets reduced by 1, so now it's x to the 4th power. What about the derivative of the second term, 17 times x cubed? This would be equal to 17 times the derivative of x cubed, where the 3 will come down, and that exponent will become 2. Now what about the derivative of 6 times x? Yesterday we saw that if we had a function of the form number times x, that the derivative was just equal to that constant multiple, was just equal to 6. And in the back we have the derivative of a constant. And yesterday we saw that if you take the derivative of a constant function, the result is 0. So after just a little bit of simplification, our derivative of this polynomial is 5x to the fourth power, plus I think 51x squared minus 6. And that's it. In that case, we have demonstrated the technique of finding the derivative of a polynomial, but it can also be used to find the derivatives of non-polynomials. For example, here we have 3 times the square root of x plus 6 divided by the square root of x. Both the square root and its reciprocal can be expressed in exponential form. So the first thing that I'm going to do is I'm going to rewrite my original function so that I can see the powers. Instead of the square root of x, I'm going to have x to the power 1/2. And instead of the reciprocal of square root x, I'll do x to the power minus 1/2. So now I'm going to calculate the derivative. And this is where you're going to begin to see me write down fewer and fewer steps. F prime is going to be the derivative of the first term, where you have 3 times 1/2, x 1/2 decreased by 1 unit. Then separately, the derivative of the second term, 6 times the power, then take minus 1/2 and decrease it by 1. So we go down to negative 3/2. And now we can just do a little bit of cleaning. F prime would be equal to 3 over 2 x to the negative 1/2 minus 3x to the negative 3 over 2. The goal, really, with functions as simple as this, is to get to the point where you can calculate these derivatives by hand faster than you could type them into a computer. That really is the goal here. Now here is a function which, at first glance, seems like it might not be possible to find the derivative using any of the rules that we have so far. The big issue is the fact that we have something to a power, but the base is not just x. So power rule could not be directly applied in a situation like this one. However, what we're going to do here is we're going to try to rewrite f of x so that it's in a format to which our existing rules could be applied. So I'm going to do what they call FOIL, or just expand it, using the formula that if you're squaring a plus b, then you should square the first term, square the last term, and then take 2 copies of first times last. So if I take 2x and square it, I get 2 squared, which is 4, and x squared, which is x squared. If I take 2x times negative 3 and double it, negative 12 times x, and then minus 3 squared will be positive 9. So now I've rewritten f of x so that it's in a format to which the sum and difference rules, the constant multiple rules, and the power rules can be applied. And again, I'm going to write very few steps. The derivative of the first term, 4 times x squared. 4 is going to be multiplied by the derivative of x squared. 2 comes down, and x to the second power becomes x to the first power. Then I'm going to look at the second term, negative 12 times x. Number times x, if you take the derivative, only the constant multiple survives. And if you take the derivative of 9, 9 is just a constant number, so 9 is going to become 0 when you take the derivative. F prime of x is just going to be 8x, take away 12. That's the derivative of this function, 2x minus 3 quantity squared. Now I know a lot of you are going to ask me the question, Sam, when we're working on homework, when we're working on a problem set, when we're working on an exam, how much work do we need to show in order to get full credit? And the truth is that I am totally fine with the amount of work that is shown right here. The truth is that in settings like an exam, I'm not going to be asking you questions that are this straightforward. The derivative is going to be something that you have to calculate in order to answer the question, but the questions will always be more conceptual than something like this. I'm going to be asking you things like, where is this function increasing? What's the slope of the tangent line? What's the instantaneous rate of change? What's the velocity, etc.? And so really the work that you're showing on the exam is, I understand conceptually why I need the derivative in this problem. That's going to be more important to me than seeing that you know the nitty-gritty of how to calculate the derivative. Because again, in 2021, most of the time, that's something that can be done pretty easily by computer. For example, here would be an example of a perfectly valid exam question. We have a function f of x equals x cubed minus x plus 4. And my job is to find all the values of x at which the graph of this function f of x is flat. Now here's the hitch. I need to give exact answers. And what this means is my answers cannot have any rounding happening at all. The answers have to be exact, not rounded. So here is why those additional instructions about giving an exact answer, why that instruction is interesting. If you were allowed to give approximate values of x where the graph was flat, that would be something that you could really just do on Desmos. You can see visually that the graph is flat at two locations. One of them is here and one of them is here. And bless Desmos, it actually will give you the location at which the graph flattens out. But it only gives you an estimate, it only gives you an approximate value of x. X is approximately equal to 0.577. But that is a rounded value that's not exact, and 3 decimal places, usually speaking, isn't necessarily even that accurate. This can, in certain applications, be a very poor estimate of the actual x value. So we're going to try and find the actual exact x value, and in order to do that, we need to do a manual calculation. So here's where I'm going to have to use my conceptual knowledge. I'm going to have to remember the fact that the graph of f of x is flat. That happens at locations where the derivative of the function is equal to 0. So what I'm really going to have to find are values of x at which the function f prime is equal to 0. So let's take this function and let's find f prime. And this is the amount of work that is reasonable for you to show on an exam. The derivative of x cubed, the power comes down, becomes 3x squared. The derivative of x by itself, we know its derivative is just 1. And the derivative of the 4 in the back, the derivative of the constant, is equal to 0. So this calculation is so simple that even I'm not really showing any intermediate steps here. But now, I'm going to try and figure out the values of x that make this derivative equal to 0, because these are the locations where the graph of the original function is horizontal. So I add 1 to both sides, I divide both sides by 3, and what am I getting? The exact answers, the exact values of x, are x is equal to positive square root 3, and x is equal to negative square root 3. Now, if you just want to confirm that your answers are probably correct, you can verify this with any old scientific calculator. And you can say, if I take 1/3 and I take the square root of that, then I'm getting the same approximate value that Desmos showed me. I'm getting the same approximate value of 0.577 that we saw on the digitized graph. So I have reason to believe that these answers are correct. But these two answers found by hand are significantly more accurate than the approximate answers that Desmos could provide. And because they are more accurate, they could be used in a lot more situations that might involve some fine movement or some really careful calculations where you have to be spot on. The sum and the difference rule, in my opinion, are relatively straightforward to use. The rule that we are about to give, though, the product rule, from time to time, students who are under stress and under pressure will end up using this rule incorrectly. So I am going to be a little bit more careful in my treatment of this rule. So the question is, the sum rule and the difference rule were incredible. If you wanted to find the derivative of a sum, you could just find the derivative of the two individual functions and add them together at the end. So the question is, does the derivative of a product behave so nicely? If you wanted to find the derivative of f of x times g of x, could you just find the derivatives of f and g separately and then multiply together the results? The answer is that, unfortunately, no. The answer is that our luck has kind of run out when it comes to rules and formulas that are really, really straightforward. If you want to find the derivative of a product, then the rule is this. You take the function f of x with no prime. This is f of x original. You multiply it by g with a prime. And then you combine that and add it with, this time the prime is on f and not on g. So as people are calculating this, you'll see them reciting this little mantra in their head. The first times the derivative of the second plus the derivative of the first times the second. Let's practice using that rule in a situation like this one. We're trying to find the derivative of the product. I'm going to say, okay, I have a product of two functions, and I want to find the derivative of this product. So the product rule says, take your first factor, don't do anything to it. Take x to the fifth minus 7x plus 6 and just copy it down to the next line. Then you want to multiply that by the derivative of the second factor. Add that to the derivative of the first factor, and multiply it by the second factor. Oh boy, it's getting squeezed here. Hold on. So to finish this problem, let's go ahead and let's calculate the derivatives that exist here. So let's calculate, for example, the derivative of the second factor, x to the 8th power plus 6x to the 4th power, etc. So we have x to the 5th power minus 7x plus 6, which is unchanged. So now I'm going to work on the derivative of the second factor, and let me just, for clarity's sake, put this in a different color. The derivative of 8 of x to the 8th power is 8x to the 7th power. The derivative of 6x to the 4th power. 4 will come down and be multiplied by 6. So 6 times 4, x to the third power. Then 3x squared. The 2 will come down and will be multiplied by the 3. 3 times 2, x to the now first power. And the derivative of the constant negative 8 will become 0 and will vanish. Okay, next let's work on the derivative of the first factor. The derivative of x to the fifth is 5x to the fourth. The derivative of negative 7x is just the minus 7. And the derivative of 6, since 6 is constant, will vanish. So the only thing that's left for me to do now is to copy-paste this original second factor to the last line. Now, importantly, this question says don't simplify, don't algebraically simplify your answer. And thank goodness, right? Because who would ever want to multiply all of this out? In general, in real life, simplification is only useful when it either increases computational efficiency or when it decreases the risk that you're going to make a typo when you enter the answer. The only thing that I might do to clean up this expression, just for the sake of my sanity, is it bothers me to have 6 times 4 here, so I'm going to rewrite this as 24. And it bothers me to have 3 times 2 here. That's an easy one to get. That's 6. So this, based on these instructions, is a perfectly valid solution to the question, find the derivative of f of x equals this monstrous product.
Boy, that escalated quickly. I mean, that really got out of hand fast.
First factor times the derivative of the second, plus the derivative of the first times the second. Now, product rule can be easy to mess up. So the typical error that I will see from students is in the following work. So we have f of x equals this product, x to the third plus x plus 1, and multiplied by 5x to the 10th minus 5. So the student will say, okay, the derivative of the first factor is 3x squared plus 1. The derivative of the second factor is 50 times x to the 9th. So the derivative of the product must be just equal to the 3x squared plus 1 multiplied by the 50x to the 9. That's not valid at all. The derivative of a product is a lot more complicated than that, as we saw in the previous exercise. The derivative of a product is not equal to the product of the derivatives. So the error was made right at the very last step, when they tried to assert that f prime could be found in such a simple manner. If I wanted to actually find the derivative of this function, I would have to do something like the following. I would have to copy down the entire first factor, which was x cubed plus x plus 1. Multiply that by the derivative of the second factor, 50x to the 10th minus 5. And then I would need to add on a second term where the derivative was on the other function. So the derivative of x cubed plus x minus 1 times the second factor. So now I could say the actual value of f prime, the actual derivative function, is equal to x cubed plus x plus 1 times 50 x to the 9th plus that 3x squared plus 1 times the entire second factor, 5x to the 10th power minus 5. This is the actual identity of f prime. Notice how much more gargantuan and complicated it is than the rather hopeful result in the wrong work. F prime here was so lovely and simple, but alas, this is incorrect. The truth is down here. As usual, we're going to do a conceptual example. So someone says, find the slope of the line tangent to this function at the location where x is equal to 1. So I'm looking for the slope of the tangent line, and I'm going to remind myself that that means I'm looking for f prime at the location where x is equal to 1. Now before I can get f prime at 1, I need to get the derivative function f prime at x. So let's find the derivative of the function f of x equals this product. So I'm going to copy down the square root of x plus 3x, multiply that by the derivative of the second function. Then add on the term where the derivative has been moved from the second function back to the first. So let's go ahead and calculate these derivatives. Here we have the square root of x plus 3x. And let's think about the derivative of x minus 3. The derivative of x will just be equal to 1. The derivative of 3, the constant, will vanish. Now moving on to the second term, this time I need to calculate the derivative of root x plus 3x. So what was the derivative of the square root of x? To get the derivative of the square root of x, remember that we rewrite this as x to the power 1 over 2. So by power rule, this will become 1/2 x to the power negative 1/2. What will happen to the 3x? The derivative of 3 times x is just 3. And then I multiply that by the unmodified second function. So this is the true nature of f prime of x. I will consent to cleaning this up just a little bit, because 1 times a quantity doesn't change the quantity. Now someone said find the slope at x equals 1. So now what I'm going to do is I'm going to plug 1 into this expression. And so I'm trying to figure out square root of 1 plus 3 times 1 plus 1/2, 1 to the power negative 1/2 plus 3 times 1 minus 3. And at this point, this is now just an arithmetic problem. So the slope of the tangent line to the function at x equals 1 is equal to negative 3. Conceptually, that would mean that the original function is decreasing. This concludes today's material. We talked about sum and difference rule, very convenient rules, which could be used to calculate the derivative of a function one term at a time. Unfortunately, product rule is not nearly so straightforward. If you want to calculate the derivative of one factor times another factor, you have to use this complicated formula where you copy down the first factor, multiply it by the derivative of the second factor, and then add derivative of the first times the second.